All right, our last section for this year, section 3.7, we're going to be looking at optimization. Optimization, it is embedded in chapter 3, which means it's related to derivatives, right? Just like the related rates were. It's an application section of derivatives. That's what it is. So optimization guidelines, kind of like we did related rate guidelines. If it's appropriate and necessary, you're going to make a sketch, a table, some kind of a visual representation of what's going on. You should identify the quantities that you know and those that you should be finding. Write any applicable equations and identify what quantity you're wanting to optimize. So optimize is a generalized word for maximize or minimize, right? So we like to maximize the space of something perhaps, or maybe we want to minimize the cost of something. Okay, that's optimize. It's a general word. And we're going to write that equation in terms of only one variable. Right, so if you're talking about area and there's length and there's width, there's got to be some way to eliminate either the length or the width in the description. Okay. You're going to determine the maximum or minimum. Right. Remember, we found that by taking the derivative, setting it equal to 0 and solving, or potentially setting it equal to does not exist in solving. That's a rarer case, but occasionally it does happen. So determining the maximum or minimum that's part 5. The maximum and minimum allowable values have to do with the constraints of the equation. For example, if you were trying to fence something in, you only have so much fence. You do not have infinite fencing to work with, right? If you're talking about profit, you have a minimum profit, or a minimum cost, I should say it that way, a minimum cost or a maximum cost. There's minimums and maximums depending on the constraints that you're working with that you have to identify that step for. Step 5, the using calculus, is where we find derivatives, set them equal to 0, and solve. Okay? So the first one we're going to do is going to be a fence. This is a very typical kind of question. You even see this happen in college algebra. You can use algebra to solve this question. I'm using it as an introductory one so that you can see how we use calculus to do the same thing. And then we'll do a couple more that are a little bit more involved. So we have a 3-sided fence that we're going to build next to a straight section of river, which forms the 4th side of a rectangular region. So it just begs for a picture right there when we stop with the first sentence, right? So you're going to draw your river, like I drew my lake last time with our fishing situation. There's my river. And I'm going to have a length and a width to form a rectangular region beside it. Okay? Nothing about scale appropriate, it's just an image. It says that the enclosed area, right, my area, is supposed to equal 1,800 square feet. It wants us to find the minimum perimeter, and we want to minimize this, and the dimensions of the corresponding enclosure. So we need some variables to represent the quantities that we have here, right? So what are some of the unknown pieces in this particular situation?
The lengths of the sides.
Yeah, the side lengths, right? And in fact, a couple of side lengths match. This is supposed to be a straight section of river, right? I didn't draw it very well. But because it's a straight section of river, and I do in fact have a rectangle, I don't care which one you call what. Maybe I'll try and make sure that it looks just like mine on my paper. I called this one X, which makes this X, and I called this Y. Use whatever letters you want. Okay, so far so good? Now there's a relationship, however, between X and Y that we know a quantity about.
X times Y equals 18.
Yeah, we know that the area is 1,800, and that's X times Y. So why does it matter? Well, it means that we're able to, in a moment, eliminate either X or Y because the relationship is that X times Y is 1,800. You had some of this happening in your related rate stuff too, where you eliminated one variable based on another quantity that you knew. So taking a look and thinking about this, our goal is to find the perimeter and find its minimum. So what is the perimeter? That is the fencing that I'm going to be using for my object.
So 2x plus 1.
Yeah. So does everybody understand why I don't need 2y?
Because that's the river.
Yeah. So it is part of the perimeter of my object, right? Like 2y would be part of the perimeter of the object, but I'm not fencing along the side that's on the river, the way that this is described. So equivalent problems often have you basing this on the side of a house or the side of an existing fence or something like that too. All right, so we only have the perimeter of the pieces that we're actually fencing in. So 2x plus y. So this is the thing that I want to minimize. Eventually, this is what I want to find the derivative of. But this isn't a rates question. I'm not doing this with dx dt and dy dt. I don't have rates here. Things aren't changing quantity values based on something shifting around. That's not what's happening. And so I need to eliminate either the x or the y. And I can do that because I know that there's a relationship right here between x and y. X times y is 1800. So it doesn't really matter which one you choose. It looks like I did y in my equation on my paper, so I'm going to try and stick with my notes today just because every time I go off of them, then I confuse myself and I write something down wrong because I look back at my notes and I'm like, no, wait, that's not the right one I was using. So if x times y is 1800, then y is equal to 1800 over x, right? Cool. So over here in my equation, I can replace my y with 1800 over x. Or, if you prefer, because we're going to be taking the derivative here in a moment, you can replace it with 1800x to the negative 1. Okay, everybody good? All right, so this section 3.7 follows what we did in chapter 3 about finding extrema, right? So we are actually finding derivatives, setting them equal to 0 and solving, or setting them equal to does not exist if that is at play in our problem. So if I find this derivative, what's the derivative of 2x? 2. And what is the derivative of 1800x to the negative 1? Yeah. So is it tripping you up just a little bit to go back to derivatives after we've done antiderivatives? I know, it does kind of. So just take it slow, make sure you get them right. All right, so far so good? Okay. So we want this to be equal to either 0 or does not exist, right? So I'll do the equals 0 first. And does not exist would be any potential denominators we have in the problem. Before I start this, though, and set it equal to 0 and actually solve, let's talk about what the minimum or maximum values of my x and my y have to be. There's sort of a reasonableness to what's going on here, right? Like, the fencing can't be too skinny or there's nothing in it. Agreed? There's no area if I have a super skinny little fence along the side of it. Agreed? Right, so my x and my y, my x is my variable in the problem at this point, so I'm going to be just focusing on x. It has to be bigger than 0. Yeah? If it were equal to 0, I wouldn't have any area at all. And a reasonable sort of, this is kind of like, it's approximately less than. That's not a real thing in math, but a reasonable upper bound might be what? 1800? Maybe 1800. It certainly seems reasonable that it wouldn't be less than that. Because if it were 1800, in fact, 1800 would give me, over here, a y value that's equal to 1. And that would also be a very skinny fence, right? If y was equal to 1? Yeah. So something in between 0 and 1800, if I get something outside of that range of values, it's not going to make any sense. Okay. So as we're thinking then about our derivative set equal to 0, we have 2 minus 1800 over x squared equals 0. We'll get a common denominator. That'd be x squared. So 2x squared minus 1800 over x squared. Obviously, this does not exist when x is 0, right? So that's a given one. The equaling to 0 on the top, however, is the part that I still have to work with. Let me shift this over just a little bit. All right, so I would like to know where 2x squared minus 1800 is actually, whoops, one more 0, is actually equal to 0 to solve the numerator. You can factor if you want. This one actually solves really nicely by shifting some things around. Namely, 2x squared is equal to 1800. If I divide by 2, x squared is equal to 900. And then when I take my square root, what happens? I get 30. Now, technically, I get plus or minus 30, but that doesn't make good sense, right? Right. So negative 30 is an option for solving this equation, but it's an option that's outside of the range of reasonable values that I established over here. I can't have a negative distance along the side of a river. So I really only have the 30 as my option. Now, here's the thing. 30 is the answer, right? I mean, like, it's my only possible answer, but I need to confirm that it actually finds the minimum perimeter. Because what we just found is that it optimizes it. or at least it potentially does. But I want to make sure that it really optimizes it and optimizes it in the way the problem actually intended. Did it really find the minimum perimeter, or did it somehow inadvertently find the maximum perimeter? Does that make sense? So I want to confirm that I found what I think I really found, and I can do that with a sign chart. Y'all remember sign charts? So with the sign chart, we put our 30 on our sign chart. We need to make sure we're picking values that are sort of reasonable, right? So that they're between the 0 and that 1800 mark. So you're going to pick a value in each one of those intervals. So pick something nice, 1 and maybe like 50 or something like that. And what you're doing is you're putting it into the derivative. So the derivative in any one of these faces right here will be fine. And you're wanting to know, is it positive, right? Is it an increasing graph? Or is it negative and it's a decreasing graph? So if I put the number 1 in here, I would have 2 minus 1800 over 1. Is that a positive or negative? That's a negative. So there's a negative that comes out if I use the number 1. 50 is a little bit more work. If I do 50 squared in my denominator, 1800 divided by 50 squared, and then 2 minus that, what do I get? You know? It's a positive. Grab your calculator and check if you'd like. The 500 squared actually makes the 1800 over the 500 squared, which would be 2500, a fraction that's smaller than 1. So we get a number that's positive. So what does it mean? Well, it means that the graph is decreasing and then it's increasing. So what happens here? It's a minimum. But that's what I wanted. I wanted to minimize my perimeter. So this is verifying all the details, but we haven't actually answered the question. So we want to make sure we answer the question. It says to find the minimum perimeter, which I haven't done. And it says to find the dimensions, which I've gotten part of that done, and I need the other part of it. So let's look at the perimeter first. Actually, let's look at the dimensions first, because then the perimeter is easier to find. So my x and my y are related right here. This y equals 1800 over x. So if x is 30, what's y? It's 60, right? Yeah? So I have my dimensions here are 30 feet by 60 feet. That's the length times the width. That gives me the correct area. And then using this 30 and this 60 in my perimeter formula, 2 times 30 plus 60, what's my perimeter? 120. So my perimeter equals 120 feet. So as you're working with these as other things as well, make sure you're using appropriate units, right? Perimeters in feet. If we were looking for area, it was in feet squared, those kinds of things. Any questions on this? Okay. The next one is like a classic example question that always shows up in textbooks. It doesn't matter who created the textbook, they're always going to have a question like this. Talks about a box with no top. It's to be built by taking a 6 inch by 10 inch sheet of cardboard and cutting X inch squares out of each corner. So what I want you to imagine is like a shoe box or a t-shirt box, okay? So if you were to cut that and you were to make it flat, you'd end up with this flat piece that's missing the corners, right? If you were to cut along the corners and you were to flatten the box out. So they're starting with the full sheet of paper. And they're going to cut out the corners. They are supposed to be square corners, X inches by X inches. So I feel like I should have made my rectangle a little bit bigger because it's going to look a little wonky, but it kind of looks more like a shoebox the way I've drawn it. And then after you cut those corners out, what you actually end up doing is you end up folding it, right? You fold it along, and I'll draw them actually in red. You fold them along these dotted lines. So this piece in this middle is now the bottom of your shoebox, and these are the sides of the shoebox all folded up. Can you picture it? Okay. So let's go back and get the details now. It tells us that we have a 6 inch by 10 inch sheet of paper. So the way that I've drawn it, this would be my 6 inches, and this would be my 10 inches. And we want to fold our box up so that it has the maximum amount of area. Okay? So this is especially interesting and valuable when you go to ship stuff. You want the box that fits the most stuff inside. You generally don't care what the shape is. A lot of things you don't care about the shape, but you need it to fit the most stuff inside. So you want to maximize the area of the inside of the box. Well, the inside of the box's area, I don't know, but I do know the outside of the box's area. What would I do to find the outside of the box's area? Like the actual sheet of paper. What's that? Yeah, length times width. And I keep saying area. It's not really area. It's the volume of the box. I apologize. But the area of the sheet of paper is 6 times 10, right? Okay. So what I need to figure out is when I fold up this box, how do I get the volume? Well, I know a formula for volume, and I suspect you do too. What's the formula for volume? For a box anyway, length times width times height. I don't know any of those dimensions, but I'm about to know a quantity that relates them. So if this length right here is 6, and I didn't mark it yet, but each of these little squares is an x by x square, then the question becomes, what is this length right here?
6 minus 2.
6 minus 2x. Yeah. So we take off the x at the top, we take off the x at the bottom. This length right here, whoops, is 6 minus 2x. And I can do the same thing to the bottom as well, right? There's this length. Again, I've got all the little squares being x by x squares. So what is this length? 10 minus 2x. That's the length and the width of my box. What's the height of my box? It's x, right? Because it folded up, and that's exactly the height that gets folded up. So over here, I have my length, which is 10 minus 2x, my width, which is 6 minus 2x, and my height, which is x, and lo and behold, I have an equation with one variable on the right-hand side, right? Volume is in terms of the variable only the variable x. What are sort of the biggest and smallest values x can be based on this picture? What's the smallest x could be? Like it can't be any smaller than 0, otherwise there's no volume at all, right? If I don't actually cut anything from the corners of the box, I don't get a box. So in terms of thinking about a minimum and a maximum value, 0 is for sure the smallest that, I can't actually even get there, right? I can't get to 0 and make a box. What is the real maximum height of this box? 10's not right. It's not 6, it's 3. How did you get 3?
Because you have to take 2x off of each side, and the smallest side is 6 inches.
Yeah, the smallest side is 6 inches. And if x were actually 3, that would be half of the length of that side. So if I have it any bigger than 3, I would not have a box. In fact, if it's equal to 3, I don't have a box either, right? So these are the upper and the lower ends of my values for x. And in this problem, it actually really matters because we're going to get a value that's going to be outside of this range. And if you go testing it, you might find things that are actually not true about the context of this particular problem. So we're going to simplify this before we take the derivative because that's really messy and I don't want to do a bunch of product rules. Sound good to you? Cool, nobody's arguing, so we're going to go with it. So thinking about multiplying this out, I have 60. This is 12 and this is 20, so that's minus 32x. And then plus 4x squared. Did I get all the pieces in there right? I think so. And then I've got the x at the end multiplied through. So this is 60x minus 32x squared plus 4x cubed. And then we're ready to take the derivative. So what is the derivative of 60x? 60. Derivative of negative 32x squared. And then the derivative of 4x cubed. Everybody good? This does have a factor in common, just a constant that I could at least minimize on my values a little bit. What number can divide all of them? So 4 is the biggest, actually. 6 doesn't quite work because 6 won't divide the 64. But 4 will work. So if I divide each of them by 4, 60 divided by 4 is 15. 64 divided by 4, 16. And then 12 divided by 4. So I'm going to spare you the trouble trying. This won't factor. In a particular problem, you're not going to know, and you would try, because factoring would be ideal if it worked. But it simply doesn't factor in this particular problem. So if something doesn't factor, what would we have to do to find out where it's equal to 0? Yeah, so you can complete the square if you wish, but quadratic formula is where we more likely are sort of tending toward your pick. So I'm going to go with the quadratic formula. This one's A, here's B, and here's C. So I definitely need to go to my next slide, so I'm going to copy this over. All right, so x equals negative b, which would be 16, plus or minus the square root of negative 16 squared, minus 4 times a, which is the 3, times the c, which is the 15, all over 2 times 3. Okay, everybody good with that? Okay. So as you're doing this, you're going to write down that step probably, and I don't expect, I mean, if you guys are in my intermediate algebra class, you would have to work this all out, right? You're just going to grab a calculator and you're going to find a decimal approximation for it. These are word problems, and while even in section 2.6, WebAssign and even the back of the book liked you to keep things in terms of pi, from a real practical sense, it doesn't make a lot of sense. These are word problems with practical application. Having values and decimal approximations is more reasonable. So we're going to continue to do that for this one as well. If WebAssign makes you put it in radical form, I'm just going to apologize in advance. But putting things in decimal form is more reasonable, so that's what I'm going to keep emphasizing. As you simplify this, there will be 2 answers that come out. They will be approximations, so I'll be clear about that. The 2 answers are actually 4.12 and 1.21. And I mentioned earlier that there would be one of them that's outside of the range of reasonable values. Which one is it?
4.
The 4. I can't have an x value that's bigger than 3, and it makes sense in terms of this particular problem. So the only potential location to optimize this particular problem is 1.21. And so we want to make sure that it really optimizes it in the way that we are expecting. So we're going to do a sign chart to show that it in fact does. So every time you're doing these problems, you're going to verify for me that it really is the maximum or the minimum you were looking for. This is part of it. You're not just going to assume, well, that's the only answer, so it must work. It doesn't always be the case, so we want to be careful about that. So here's my 1.21. I need something that's between 0 and 1.21 and between 1.21 and 3. And of course, the nicest values are 1 and 2, right? Yeah. So we're going to put the 1 and the 2 into the derivative, and this part of the derivative is just fine if you want to use it. The simplified where we divided by 4, the division by 4 doesn't change signs at all because it was dividing by a positive. So if you want to use that version of it to find out, do I have positives or do I have negatives, you can. So as we do that, you will put the number 1 in here. So 15 minus 16 plus 3 gives you a positive. And if we put in 2, we'd have 15 minus 32 plus 12. And I would actually end up getting a negative. So you're going to substitute these values into the derivative. That's how we always do sign charts when we're looking at finding out whether or not we have a maximum or minimum. So this graph then is increasing and then it's decreasing, which means I have a maximum. What was I looking for? A maximum. I wanted to maximize the volume. So I have in fact maximized the volume. The x that I was looking for is 1.21. But I need to make sure I answer the question. It said find the value of x that maximizes the box. We did that. So we actually answered the question by finding the x is approximately 1.21, but it's 1.21 what? Inches. So I want to make sure we put our units appropriate in there. In particular, you saw the example, I hope at least that you looked at the example of the pooling oil, the last 5 minutes of it I did after you guys left, and saw why it is really important to pay attention to those units because they don't always match within a problem. Same thing for the end. We want to make sure that the units actually make sense in terms of our problem, and we have our 1.21 inches. All right, we're going to do one more. The last one is sort of the least applicable, but it's the most interesting from a geometrical standpoint. In this particular one, we have a curve. It's basic parabola. You're super familiar with this guy. You've been using him for years, right? And we're trying to figure out what the point on the curve is that is the closest to the point 0, 1. So I'm going to draw the shape that they're referring to, although I know you know it. So we have our basic parabola shape, something like that. And the point 0, 1 would be right here. So there's infinitely many points on this curve, right? Like one of them is here. This is not the closest point to the point 0, 1, right? You might think, well, I could go straight in either direction and have a viable option. And in fact, that sort of seems like a reasonable maximum and minimum location, doesn't it? The distance to the left, the distance straight down, and my answer is probably somewhere over here, in the middle. Agreed? So this is the ordered pair that I'm looking for. That's the point I'm looking for, is this location that I don't know what it is, but it's right here. What am I actually trying to maximize or minimize? In this case, minimize.
The distance between the points.
Distance. So I'm trying to minimize, it doesn't even have the word in here, but I'm trying to minimize the distance. I should spell it right. I'm trying to minimize the distance. So we're going to use the distance formula. So this is one of those ones that I kind of think you should know the distance formula. You've been using that one for quite a while as well. So what is the distance formula between 2 points? We'll just use arbitrary points for the moment, x1, y1, so that you can remember that formula, and x2, y2. What's the distance between those 2 points? Okay, so let me remind you in case you have forgotten this one. We're looking at the difference in the x values squared, the difference in the y values squared. We add them together and we take a square root. It doesn't matter the order because when we square things, the order becomes irrelevant. 5 minus 3 is the same as 3 minus 5 if I square both those values, right? So it doesn't really matter if I write x1 minus y x2 or x2 minus x1. But the points that I need are present over here in this particular problem. This point, ordered pair, is 0, 1. That's one of my ordered pairs over here. I don't care which one you use it as. I'm just going to use it as the second one. So that's the x2, y2 in my problem, is the 0, 1. The other one is the xy. But as you can imagine, that's not super helpful because that would leave 2 variables in my problem. So let me write out what I have so far, and then we'll talk about how we can eliminate one of those variables. So this is a square root. It is x minus the x value of 0 plus y minus the y value of 1. But there is a relationship between x and y in this particular problem.
Y equals x squared.
Y equals x squared. It's the equation, right? Whatever this point is, there is a relationship between x and y. Y is equal to x squared. So in the problem, I can replace the y with the x squared quantity. So over here, this is now just x squared by itself because I've subtracted, okay? And then I have plus, and then I have x squared minus 1 squared because y is x squared. I'm always looking for a relationship between the quantities, and it will always be there. Sometimes you have to work a little harder for it. Sometimes it might be a little bit more obvious. Okay, but that's a mess. So let's clean it up. So I have x squared. Remember, you're going to FOIL this out. So x squared squared would be x to the 4th. The inner and the outer terms are going to give me negative 2x squared. And the last term is going to give me a positive 1. So this one and this one will combine. So now I have the square root of, and I'll write it in descending order, x squared plus, x to the 4th plus x squared plus 1. Yes, minus, thank you. Get my signs right. Thanks for keeping me on my toes, you guys are doing great. Okay, so far so good? Okay, I have some upper and lower limits I need to establish on this x. I'm going to set it equal to 0 and solve, but I need to kind of get some bounds. So how far away, maximum, minimum, would x be? Remember the distance. I shouldn't say the distance. The x value is the length right here. I've got so many colors on my screen. Let's go with some blue. This is my length for my x, right? It's how far I am from this beginning to this. What is the minimum value for x? 0, right? Because that would be coming straight down. And if I swung all the way over here, what would be my maximum for x? It's 1. So my x value is going to be somewhere between 0 and 1 for it to make sense. All right, so we're going to take a derivative now. I'm going to run out of space, so let me go to the next slide. Keep getting random stray marks. Let's try one more time. Okay. So what is the derivative of the square root of x to the fourth minus x squared plus 1?
1 half x squared plus 1 to negative 1 half times 4x cubed minus 2x.
Okay, so that's what Alyssa said. Does that look good? Okay, the square root part's going to go into the denominator, so it will not be able to set equal to 0, but it will potentially have a location where it doesn't exist if that were to be useful. X cubed minus 2x on top. Oh, even better. Do you see it's going to divide by that 2 over there? X to the fourth minus x squared plus 1. So this will simplify here with the 2. So I actually would have 2x cubed minus x over the square root of x to the fourth minus x squared plus 1. This denominator setting equal to 0 is not going to lead us anywhere. Just going to throw that out there. We could try and you could work with it. But the numerator set equal to 0 will. So we're going to work with that in the efforts of saving a little bit of time. I'm going to spoil a little bit of the fun. So I want to set this equal to 0. What would I do? You'd factor, and you'd factor out an x, yes. So that would leave me with 2x squared minus 1 equals 0. Obviously, x equals 0 is one of the values, which is a lower end anyway, so it doesn't really give us any helpful information. But the other piece will. 2x squared minus 1 equals 0 means that I have 2x squared equals 1. X squared is equal to 1/2. And if I square root it, what will I get?
1 over the square root of 2.
Yeah, so technically get plus or minus, but I don't need the negative, right? Because my limits of on x are between 0 and 1, so I only have the positives. So I have a square root of 1/2, which mysteriously enough is square root 2 over 2, which should be a familiar-ish value to you. Where does that square root 2 over 2 show up? On the unit circle. Do you remember what angle measure it shows up at? Pi over 4, which is equivalent to 45 degrees, right? Does it make sense from a picture point of view that this angle would be a 45-degree angle?
Yeah.
Yeah, that should make sense, right? That's what's happening here, which is very interesting. Now, we haven't verified that it really gives us our maximum minimum values. We need to do that. But that's our value that we're looking for. So we're looking between 0 and 1, and we have the square root of 2 over 2. Square root of 2 over 2. Somebody give me an approximation. What is it?
Less than 1.
I hope it's less than 1. Is it?
0.707.
All right, 0.7. So we need numbers to pick on either side of 0.7.
0.5.
0.5 sounds good. Oh, I need a red. That orange is too light.
0.75.
0.5. 0.75. Sure. Or you could use 0.8 or something else. And you're going to test each of those values in the derivative. And the derivative needs to be tested. So you have some choices, but honestly, you only need to test it in the numerator. Why would I not really need to test it into the denominator here? Yeah. The denominator is always positive, right? Because it's a square root. with me? So we really only need to test it into the numerator. If you test it into all of it, that's fine, but you're not going to get any other information by doing so. If we put this in, we're going to get a negative, and then we're going to get a positive. That's what it will end up being. What does the negative do?
It makes it downward.
It makes it go down, and then the positive makes it go up, meaning that this is a minimum. Now, it's very interesting for us to note that we limited ourselves only to considering half of this graph, but this graph has symmetry, right? So there's actually 2 points. Yeah, it's actually the exact same thing. We don't really have to do the extra work to even find it because we know what symmetry looks like on this graph. It's parabola. So we get the other point kind of for free by recognizing that feature. So we're looking for, oops, I flipped back over here, the point. So far, we've only found the x value, and we found 2 of them. One square root 2 over 2. The other one actually is negative square root 2 over 2. How will I find my y value?
You plug it in.
Plug it into what?
To the equation.
Not distance. The equation, the relationship, yeah, on the curve. So what happens when I take the square root of 2 over 2 and I square it?
You get 2 over 4.
Which is
1/2.
1/2. In particular, it might be easier to think of what happens when I take the square root of 1/2 and square it. Right? Yeah, so I do get 1/2. So there are actually 2 values whose distance are minimized because I have a symmetric curve, right? A symmetric graph on the x-axis to that 0.01. That's special to the 0.01. That would not necessarily happen at any arbitrary point, right? Or any arbitrary graph. It's special to the situation because of the symmetry that's going on.
If you had expanded the 0, then we would have just found it.
Yes, yeah. Yeah, if we had done this and we had recognized or thought about it over here as that we're going between -1 and 1, we would have allowed the negative square root 2 over 2, and we would have had a little bit larger of a graph, and that would be totally fine too. The symmetry meant that we didn't have to do it that way, but we could have. All right.